Today about chemical, huh? So let me do I will record, okay? So I will record this lecture for people who cannot attend. Okay. So that they can go any time. Last week we talked about chapter. Why chapter 2? We are now chapter 3. This chapter 3. Very sorry. This chapter 3, huh? Okay. Last week we talked about physical. Can you see pointer or no?
Yes, sir, can.
Can bully, okay, alhamdulillah, okay. So last week we talked about physical and we know how to calculate now suspended solids because we have different suspended solids. We have at least 5, right? And then calculation will be different. We have different equations and different categories of suspended solids. Suspended solid can be calculated after drying and then after ignition. And from the equation, we can know the percentage and how much dissolve suspended solid, how much volatile suspended solid. All this we can calculate it from last chapter, chapter 2. Today we'll go for chemical. If you have any question, you can ask. You can raise your hand and ask, no problem, anytime, okay? Primary, last time we talked about primary. Primary mainly, as you know, it is for physical. So this we done last week with some exercise. Okay, this also primary clarifier with settleable organic. And then we go for secondary. Secondary will be actually not only chemical, sometimes biological also included, but biological I will try to make it in chapter 4, next chapter with problems. So here I will focus only about chemical treatment. This aeration considered actually to be both chemical and biological, but we will focus only about chemical in this. And secondary will be aeration, secondary clarifier, and then chlorine for disinfection, and then effluent. Here we add chlorine. Here O2 means aeration, or this anaerobic bacteria will work here to form sludge rich with bacteria and then can be retained here. So here we will focus as you see here, for example, this is primary, and then we go here. Primary clarifier, sometimes there is removable settable can be here by settling, but sometimes you have very minute particles, very small particles. That is called nano-sized particles. Cannot be precipitate by gravity naturally. So what we need to do in this case, we need to do coagulation. And coagulation, what is the job of coagulation? Small particles or nano-sized particles will gather together, and because became bigger because of gravity will settle. But here we need to add coagulant, sometimes liquid, sometimes powder. If you know alum, it is okay. If you know also there is aluminum sulfate powder also, or in term of liquid also okay, or ferrous sulfate also bole. Other coagulant like what we have done in Makmal last time, we use maybe fly ash, waste from fly ash. Maybe Shahida, she did last time experiment in details about fly ash coagulation for palm waste from palm oil industry. Okay. And in this, we need to calculate how much chemical oxygen demand, how much dissolved oxygen, and etc. This how to calculate, we will see in details the method how to calculate. Coagulation process was described in another time I ask you to see Salahuddin image. You can see for, I think you already saw before, but if you don't understand coagulation, you go there and see one more. I think in the list you can find coagulation, okay? And real industrial example, I give you also one lecture, maybe number 2, about Si2 removal. That is from real industry. That microelectronics and became like milky color. Milky color, this is like cannot precipitate. If you give it for 1 year, 2 years, because silica is very strong, cannot be degraded. So what we are doing in that slides, we add coagulant and then we remove by adding coagulation. I think this, if you go to WhatsApp, I send you 17th May. You have this lecture or no? Do you have or no? Hello?
Yes, sir.
Can you hear? Do you have or no? This lecture about SiO2 removal. I send you by WhatsApp. So if you want details of in this how in real industry we apply coagulation. Okay.
Okay.
All right. If you don't understand, you can go back because this is recorded. So anytime you can watch. Or you can download because I will delete because I have limited capacity. So once we finish, you can download to see anytime for you. Chemical parameters, we have alkalinity. All of you, you know alkalinity, and that is means that the pH value will be very high. And this comes from hydroxide, carbonate, bicarbonates, and elements such as calcium, magnesium, sodium, potassium, and ammonia. Okay? So this we measure alkalinity by what? pH meter, right? So by training against standard acid, and the results are expressed in term of calcium carbonate, milligram per liter or part per million. Last time I show you how we prove that 1 milligram per liter will equal 1 part per million. But usually we determine this one by pH meter. Alkalinity, there is another thing called hardness. For chemical, we know how to calculate hardness from magnesium and calcium, and we can calculate total hardness. We will see in the example later today, inshallah. What is pH? pH also has relation to alkalinity and acidity, which is the negative log of the hydrogen ion. This is the equation, how to calculate pH value. And how we measure pH value, we have here pH meter. Very easy, no need. We need just to make calibration because sometimes this reading will be changed. So we need to make calibration. We make two standards, one acidic, one alkaline, and then after we adjust acidic and alkaline, then we measure the real sample and will give us the real pH value. Okay. Dissolved oxygen. What is dissolved oxygen? It is the amount of molecular oxygen dissolved in water. It is required for the respiration of aerobic microorganisms and also for in marine for fish and plankton and for other how to say other species in marine environment. However, oxygen is only slightly soluble in water. It's not too, maybe maximum 15, 20 part per million, not more than that. The actual quantity of oxygen, other gases too, that can be present in solution as given by the solubility of gas, the partial pressure of the gas in the atmosphere, the temperature, the concentration of the impurities in the water, salinity, suspended solid, and etc. Determination, how we determine? By something called dissolve oxygen meter. If you can see here, also will give you part per million. Okay. Biochemical oxygen demand. This I plan to talk in details in next chapter, next week or next week, and we give some problems about biological oxygen demand. But what is biological oxygen demand? We make here just very short. Some parameter and the amount of oxygen required to oxidize organic matter present in the water biochemically. So BOD is an indirect measure of the concentration of organic contamination in water. Okay. How we do the experiment? I think experiment done in incubator. We put the sample inside one of these bottles, and then we put here at 20 degrees centigrade. And every day for 5 days, we have to measure dissolved oxygen. If there is bacteria or microorganism, this dissolved oxygen will decrease day by day because microorganisms will consume some of this oxygen. This is actually it's called BOD track, and it is very sikat mahal. But here no need to bring sample every day and measure dissolved. This will be automatically run here. You can see in the screen here. You can see every day dissolved oxygen for each bottle. You can make up to 6 bottles. So you can measure 6 samples at the same time without bringing out, because in our makmal, in our laboratory, we don't have this instrument. So we have only one. We have incubator, yes, 20 degree we keep, but this we take out every day and measure dissolved oxygen and bring back and we measure. With this, go and back and open and close. Dissolved oxygen also come sometimes to inside this bottle. So your results will not be very accurate. But with this instrument, no need to bring out. Everything will be here and close all the time. So you go from this screen, you take all dissolved oxygen reading. And then we calculate how much BOD. Hopefully you understand. We go to chemical oxygen demand. The equivalent amount of oxygen required to oxidize organic matter present in water sample by means of strong chemical oxidizing agent. It's like KMNO4. We add to the sample and we give too much heat for at least 30 minutes. And then after that, we measure by UV, by UV detector, or we call it sometimes hatch track. We set the wavelength for COD, and then we can get the readings. But also we need to have standards. Otherwise, this instrument is blind, cannot tell us any information unless we have standards. So we get the accurate and reliable results. Okay. What about total organic carbon? Total organic carbon, somehow it is close to COD, but here more wide. So TOC test is especially applicable to small concentration of organic matter. Wastewater content of carbon bond in organic molecules in the TOC comprises nearly all carbon compound except a few carbon species which are looked at as inorganic carbon dioxide, hydrogen carbonate, cyanide, and so on and so forth. So here also will give you indication about how much organic compound in the sample. Like petrochemical industry will be rich with this total organic. How we measure? Also there is instrument to measure total organic carbon. What is the relation between BOD, COD, and TOC? You see here, this is the table correlation between both or 3 parameters. It gives you here type of wastewater untreated. This will be between BOD over COD will be 0.3 to 0.8. BOD to TOC from 1.2 to 2. And then here after primary settling, you see will be secret higher here, or 0.4 to 0.6 here less, here more or less final effluent. Okay, so decrease with treatment. Okay. What is inorganic nitrogen is present in the oxidized form like nitrite, nitrate, and reduced form ammonia and ammonium and dinitrogen gas. Organic nitrogen is available in variety of complex forms such as amino acid, protein, humic acid, and urea. Okay, and phosphorus. Usually, nitrogen and phosphorus coming from the fertilizer as fertilizer from agricultural waste. You will have nitrogenous and phosphorus compound is very rich. How to measure this? Also, we need to make analysis through Hatch by special wavelength, and we have to add some chemicals, and then finally we can get total nitrogen and total phosphorus. I think some of you did this experiment. Okay, we go to problems related to chemical parameters. I hope you follow here carefully. Try to understand. If you have any question, you can ask. Okay, we go to Dulu periodic table. Why periodic table? Because we need from here to differentiate between atomic number and atomic weight. From where we get atomic number, from where we get atomic weight. Okay, so here this will be periods. This how many? 1, 2, 3, 4, 5, 6, 7. So this is first under group. So I have how many groups? I have 18. So the first group here, equivalence is positive 1. Sorry. Here will be positive 1. Here will be positive 2. Okay. Opposite side here will be, this is, as you know, this is saturated. This is noble gases here. Here will be -1. Here will be -2. This is equivalency. Yeah? What is equivalency? We will see in the next slide. Okay, but this is very important because if you have elements here, you understand that the equivalence will be here 1. Here will be 2. Here will be, this is +1, +2. Here will be -1. This -2. Here it is saturated, means that it cannot accept more electrons. Okay. Here we go to this sign here. If you see, for example, we take sodium because we are very familiar with sodium. Here, this is 11 will be the atomic number, huh? Atomic number. Okay. And here we go here, it is atomic weight. This one will be atomic weight. Okay. So up here will be atomic number, or here atomic number. Here will be atomic weight. What is the difference between atomic number and atomic weight? Usually atomic weight will be 2 times, not all elements, but almost will be 2 times atomic number. For example, this is 11. This, as you see here, 23. So almost 2 times. For example, this is 19. This is somehow 39. Okay. So here, those elements all equivalency will be +1. How +1? We will see in the next. Do you have any question? Other question? I hear someone is talking. Anyway, this one is +1, +2. Here will be -1, -2. And why +1, +2? We will see in the next slide here. For example, if we have sodium chloride and we dissolve in water, this will be ionized. This will be Na positive ion and Cl negative ions. Will be like this here. Will not be powder anymore. Will be dissolved and became ions. Okay? Understand or no? Or we call it sodium aqueous, chloride aqueous, or chlorine aqueous. Okay? Why this became negative and this became positive? I think next slide will show you. Okay. As you know, sodium, as we mentioned in the previous, it has 11. Okay, we go back. Previous. Sodium here have 11 electrons, right? So it has 11 electrons. And we know that in the nucleus, electron must equal proton, right? So if it is 11 in the here in the outer orbit, it takes only 8. In the first will take 2, this will take 8, so extra 1 will be, because you have 11. So here 11, it is unstable, so sodium preferred to bring this to another element. If we see Cl here, how much? Cl is 17, right? So 17, that it means that it needs 1 electron to fill the outer orbit. So it receives from here. So here, sodium gives 1 electron, became only 10. So here 10 electron, here 11 proton. If you make summation, you will get 1 proton extra. This is why here you have positive ion. Hope you understand. For chlorine, you have here 18 electron. Originally only 17, but it takes 1 more from sodium, became 18. So you have 18 electron, you have 17 proton. If you take summation, you will get 1 electron extra, or negative electron. This is why Cl became negative. سكت فهم؟
Paham, sir.
Somehow clear.
Okay.
You can go back to the slide and check one by one, huh? But this is, I want you to understand why here previous. Why here this is here negative, and why here positive. Here negative because it release 1. Here will be positive because it release 1 electron. So will remain 1 proton extra. Here 1 proton extra, here 2 proton extra. So magnesium will be 2 plus, calcium will be 2 plus, but here sodium will be only 1, potassium will be only 1. Here if you go to ClF, bromide, iodide, all those elements will be -1. Why? Because it takes 1 more electron. It takes 1 more electron, so became minus. Here also it takes 2 more electrons, here became also -2. This will be 4, this will be 3. Hopefully you understand. Okay, we go to our calculation. What we mean by electroneutrality? This I send you the first lecture notes I sent to you. What is the principle of electroneutrality? Requires that the summation of the positive ion when I dissolve sodium chloride in water supposed to be cations, which is positive ions, must equal anions, which are negative ions. If not equal, meaning that there is something wrong. Okay, so this one will be cations must equal anions. Okay, what is cations? It is the positive charge. Anions is the negative charge. What is the equivalent weight? Will be the molecular weight divided by Z, divided by equivalence. For example, if it is calcium, this is equivalent weight, will be molecular weight of calcium divided by 2, meaning that will be 40 divided by 2 will be only 20. Okay, if we are talking about Cl, Cl is 1. So molecular weight will be 35.5 divided by 1 will be 35.5. Understand? If we have sodium will be 23 divided by 1 will be 23. How to calculate percent difference? Will be summation of cations minus summation of anions divided by summation of both multiplied by 100. Okay, then you will get the difference. Why this is very important? Because we want to know our analysis, it is accurate or no, it is true or no, or it's something wrong. Okay, we see example to make you understand more. Okay, try to not to sleep here, try to open your eyes and follow slowly. Here I have analysis. I take one sample from waste and result were obtained from for 4 water samples. I give here only one. Check the accuracy of the analytical measurement of the water. Do you suspect that a constituent of significance has been neglected? If so, is it cations or anions? And calculate the total hardness. Okay, so after analysis, I got here calcium 1 to 1.3 milligram per liter or part per million. How I calculate this? Calcium, magnesium, potassium, sodium, potassium. I use atomic absorption. So I will get these results. Okay, so I take one sample here and make analysis for cations. I got those results. I make analysis for anions. I got those results. All in milligram per liter or part per million. So how to check my analysis is okay, or how to calculate the total hardness? We see one by one, step by step. Okay, this is the table, nothing here. But here you see here component. I make the component calcium, magnesium, potassium, sodium, potassium. Okay, concentration I have here. Molecular weight, how much? 40, 24, 23, 39. From where this one? This is from periodic table. Okay, clear? Molecular weight,
Yes,
I take it from the table. How to calculate equivalent weight? I will take this one, molecular weight, divided by charge, by equivalence. Here, 40 divided by 2. Here for magnesium, 24.3 divided by 2. For sodium, 23 divided by 1. For potassium, 39 divided by 1. So I will get this results. This is, I call it equivalent weight or milligram per milli equivalent. All right? Bole tabule. I go now to calculate how much milligram per liter. What I do is, I will divide concentration milligram per liter divided by milli equivalent. I will divide column 2 by divided by column 4, and I will get those results. For calcium will be 1 to 1.3 divided by 20.03. I will get this value. For magnesium, 36.2 divided by 12.15. I will get 2.97, and then so on and so forth. And then I will make summation of the total. This I call it, because it is positive, I call it cation or anions. I call it cations, okay? Please don't confuse, okay? So summation of cations will be 9.68. How I get, this is the steps, okay? I go to anions and I will try to calculate. For example, HCO3, is it 1 or 2? It is 1. How I know? For example, if I have this, better to combine with acid. You know very well H2SO4. So meaning that SO4 will be 2. HCl, so meaning that Cl will be 1. NO3, HNO3, this also will be 1. This also HCO3H, this also will be 1. So this will be 1, this will be 2, this will be 1, this will be 1. This is all negative ions. Okay. Concentration, how much I have? I have 280, 116, 61, 15.6 milligram per liter. Okay. Molecular weight of HCO3, how I can calculate? I will calculate H1C1O3 3. So this is H1, C is 12. So 1 plus 12, 14. And this is O3. For O is 16 multiplied by 3. So how much I will get? Then all summation will be 61. Is it clear? Clear.
Yes, sir.
SO4 also, this is 32 and this is 64. If I calculate all together, I will get 96. For Cl is 35.4. This actually 0.5. NO3 is 62. From where I get all this? Also from periodic table for each element and make summation for all. So I will get those values. How to calculate equivalent weight? I will go again, divide concentration divided by molecular, sorry, how to get dulu equivalent weight? I will calculate this concentration divided by, equivalent weight will be molecular weight divided by equivalence. How much? This equivalence is 1, so will be same, not change. SO4 will be 2, so meaning that I will divide this by 2. For Cl is 1, so it will be the same. For NO3 is 1, will be the same. How to calculate milligram per liter or total anions? I divide concentration divided by equivalent weight. I will get milligram per liter. So I calculate for HCO3, it is 280 divided by 61, we'll get 4.58, and then 116 divided by 48, you will get 2.41, and then 61 divided by 35.4, you will get 1.72, and then NO3 you will get 0.25, and I will take the summation. So what you notice here from the summation of cations and anions, it is not the same. There is difference. This is 9.68, this is 8.96. So do you think it is okay or not okay? Because we said that when we have dissolved solution, completely dissolved, positive ions must equal negative ions. But here, we don't have positive positive ions equal negative ions. There is some. So what is the reason? Maybe we discuss later about the reason. Maybe analysis, maybe we will see. Is it clear this table how to make?
Clear, sir.
Clear, alhamdulillah. We go to next, how to make the chart or the bar. For cations, I say 9.68, right? So I will go here, I will make calcium how much? 6. This is by scale. You can make 6.05 centimeter bole, or you can make it as you like, maybe millimeter also bole. It is up to you. Okay? And then I will add to this 6.05 plus 2.797 will be up to here. And then I add, and then I add. So this line will be for cations. All right? So if I add this one plus this one plus this one plus this one, I will get the total summation of cations, which is 9.68. Is it clear how to make this table here?
Yes, sir.
Clear. I will go to anions. I will make the same scale. Don't make different scale. If you make different scale, will be big masala, big problem. You will not get good results. You will have mistakes. Okay? So you go for HCO3, it is 4.58, meaning that it is less than 6.05. So cannot go to here. Will be lower, right? So you make line here. So this area will be HCO3. You go to next one, SO4 will be 2.4. So you add 4.58, 2 will be somewhere here. You add 1.72, you will get somewhere here. You will 0.25, you will get somewhere here. And this summation all will be 8.96. See, this line or this bar is not equal the same bar. Cations doesn't equal anions. Okay, is it clear how to make? Very easy. Just you have the components. You put each one in bar. So you put the concentration, how much concentration, and you summation. You take the first one plus second one, first one plus second one plus third one, and then first one, second one, third one plus fourth one, and then you make your here you make your table, huh? Okay, and then you go similarly. You make the same for anions. You will get this table. I think for chemical, tada masala tabi for polymer, they have some, but you can ask privately. I will answer you, inshallah. Or you ask, if you have one from chemical, you can ask, inshallah, you will understand. I think very. So how to make hypothetical combination? It is very, very easy. Once you establish this table or this bars, you will go here. Here, calcium. Here will take part of HCO3. So you will have CaHCO3. This Y2 because calcium is 2 equivalents. Calcium or HCO3 is 1. So this will be Ca1. This will be 2. So here will be CaHCO3 all 2. Okay. Here calcium not finished yet. Still other here. So this part of calcium will go with SO4. Will make CaSO4. Part of SO4 still there, not finished yet. So we'll go to react with magnesium to form magnesium sulfate. Okay. So we'll make MgSO4. Oh, sorry, this is mistake. Wow. This is mistake actually, very sorry. This is here 4, here 2, okay? All right, will be like this, SO4, 2. This also MgCl2, okay? This also calcium SO4, 2. This will be like this because calcium is second, huh? And then magnesium nitrate, this will be 2 also. And then see here, magnesium sulfate, magnesium chloride, and also magnesium nitrate, other. So these 3 anions will react with magnesium. So here, sodium also still left NO3. So will be NaNO3. Okay. And then for potassium, nothing left. So you will have anything here in the hypothetical combination. If I change the order, I will get another combination. It is okay. This is just to show you how, based on your arrangement. Okay. Question is, what is the reason? Why it is the accuracy not sufficient? Because here cations 9.68, anion 8.96. This is because attributed to the missing of significant concentration, not analyzed. Maybe we make analysis by atomic absorption, but we cannot detect all elements. Maybe we don't have some problem with instrument. Maybe instrument analytical error, maybe human error during dilution, during preparation your samples, you make some errors. So as a result, you will get here some mistake and others. So if you have cations and anions, if you completely dissolve samples, supposed to be equal. However, if not equal, those may be the reasons. Those are maybe the reasons. Okay. All right. We go to another exercise to make it more clearer. We calculate the accuracy. How to calculate the accuracy? We said that 100 summation of cations minus anions divided by total cations and anions, and I will get here 9.68 minus 8 point divided by total, you will get 3.86. This result is considered to be very good actually, because up to 5% and sometimes maximum 10% we can accept. The cation anion balance is not of sufficient accuracy. The reason might be attributed to we mentioned before. Okay. And how to calculate the total hardness? We take calcium and magnesium. Calcium and magnesium, we see calcium and magnesium previous. Calcium, this is calcium. and this is magnesium. So 6.05 plus 2.97. Okay. So you will get here summation of calcium and magnesium, and we multiply by equivalent weight of calcium carbonate. Calcium carbonate, this is molecular weight is 100, equivalent weight is 50, half, because this is calcium second. So this will be multiplied by 50, not 100. I will get 451 milligram per liter or part per million. How? Okay, clear. Hopefully you understand.
Yes, sir.
Hopefully you can, when you study back, you can follow. Okay. Example 2, also I will give you another example, checking the accuracy of analytical measurement. The following analysis has been completed on a filtered effluent from an extended aeration water treatment plant that is to be used for landscape watering. Check the accuracy of the analysis to determine if the analysis is sufficiently accurate based on your standing for analytical chemistry. Okay, so I have here cations, give me the concentration, and give me anions concentration. So here I will ask you calcium here, positive or negative here, Dulu? Will be positive because it is in the left side. So will be here. Calcium, it is first or second equivalence? It is second. So here calcium will be plus, plus. Magnesium also will be plus, plus. Sodium will be 1, potassium will be 1. Plus 1. Woman is driving. Okay. For anions here, HCO3 will be 1. SO4 will be 2. Cl will be 1. NO4, NO3 will be 1. And those are negative. All right. How to know it is negative or positive? I can know from if I combine this as acid. HCO3, H, H2SO4, HCl, HNO3. So here 1, 1, 1, here 1, 1, 2, 1. So I can recognize the equivalence. It is first or second or third. If aluminum is 3, because it is in the third column, okay? In the third column after, from the right, yeah, from left, okay? Here, we prepare the cation anion balance. This is in your, it is already solved in your lecture notes, but here I will repeat for you one more time. Here, concentration, here milli equivalence, milligram per milli equivalence. Here calcium will be not 40, will be 20, here already divided. Here magnesium will be divided. Sodium will be divided by 1, will be 23, potassium will be 39.1. Okay. Here I calculate milli equivalent per liter or milligram per liter also. I divide this one concentration divided by milligram per milli equivalent. So I will get those concentration. For anions also I will do the same, similar way. I will get also milli equivalent. Here also you see here 7.99, here 8.27. Not exactly the same, but however it's not very far. Huh? So how to calculate the accuracy? As I told you, we calculate, here will be minus 1.72. It is plus or minus 5%, it is acceptable, no problem. For a total cation concentration between 3 and 10 milli equivalent, the acceptable difference must be equal or less than 2%. Okay, see here, it is less than 1%. Therefore, this analysis somehow accurate. If not accurate, results, what is the reasons? Reasons may be attributed to the following problems. Maybe missing of significant concentration not analyzed, instrumental and analytical error, human error. Human error means careless or not accuracy. When you make, for example, when you make BOD analysis, You open the bottle very long and oxygen go inside, and that gives you error. When you make a measurement for BOD, you're supposed to take and close immediately so that oxygen will not go inside. So this kind of human error that sometimes difficult to control because you must open anyway. But difference between one very good trained students who open very fast and close and not make space, and one just open and talk with his friend and let oxygen go and then measure. There is a big difference between both students. Both accuracy will not be the same. We go to example calculation of theoretical oxygen demand, or THOD. TH is mean theoretical oxygen demand. I have here glycine compound using the following assumption. The first step, the organic carbon and nitrogen are converted to carbon dioxide and ammonia. So this compound changed to carbon dioxide and ammonia. And then in the second and third steps, the ammonia is oxidized sequentially to nitrate, nitrite, and nitrate. Number three, the theoretical oxygen demand is the summation of the oxygen required for all three steps. So how we can solve this problem? First of all, we need to make balanced equation. I think you study stoichiometry in the elementary principle of chemical engineering. And in pollution control also we do some exercise like this one, maybe the same. For polymer, I think if you follow, I think you can understand more. No problem. It's not a big issue. So how to make balanced equation? First of all, we see from the step. He said 3 steps. First step is compound oxidation change to NH3 and carbon dioxide. Of course, here will be H2O there. So how to make balanced equation? We need to calculate how much carbon here in the left side, how much oxygen in the left side. Right side must equal left side. So here I need to multiply by 3/2 O2, and then here multiply by 2. Then I will get balanced equation. Okay. So first thing is how to write balanced equation and how to make it balanced. Okay. Write balanced reaction for the nitrogenous oxygen demand. NH3 here will react with oxygen to produce HNO2 plus H2O. This H2O, HNO2, again will react with oxygen to produce HNO3. If I make summation here, I will have NH3. Okay, here 3/2 O2 plus half O2 will give me 4/2, which is 2 O2. As here HNO2 produced in A will consume in HNO2B. So this will be 0 because here produced, here consumed. Okay, plus H2O. This is H2O, here HNO3. This also must be balanced equation. If you check, it will be, if not balanced equation, it will be not correct. You need to make it balanced equation. If you check here, for example, here H3, here you have H, here 2, it will be 3. Okay. O2, here you have 4, here you have 3, plus 1 will be 4. For N, you have only 1 here, you have only 1 here. So it is okay. So how to calculate theoretical oxygen demand? I will see how much oxygen needed here in the first and in the second, right? In the first here, this one, and in the second. So here, how much I need oxygen here in this step? I need 3/2, and in this one I need 2 or 4/2 to make summation. Okay. So here plus here needs for 1 mole glycine. So this, be careful. This is not weight. Here we are talking about mole. If you want change from mole to weight, I need to multiply by molecular weight. I think we did too much in pollution control, how to change from weight to molecular weight, from molecular weight to weight. But here, make sure it is moles, not weight. Okay? So here will be 3 over 2 plus over 2. This is moles oxygen needed for 1 mole glycine. I will get 7 over 2 mole O2 divided 1 mole glycine. If I multiply by 32, this is molecular weight of O2. I will get 112 gram O2 divided by mole glycine. If I want to change this gram to kilogram here or gram again, I need to change this mole glycine to gram glycine. How? I need to multiply the molecular weight of glycine. How to multiply the molecular weight of glycine? I need to calculate how much carbon I have. 1, 2. So it will be 2 multiplied by 12 will be 24. What about H? I have here 2. I have here 2 will be 4. 4 plus 1, 5. So I have 5H. So 24 plus 5. If I go to N, I have here only 1 will be 14. So add to the previous one. What about O? I have here 2 will be 16 multiplied by 2 will be 32. And I add all those and I multiply here to change from mole to gram mole. Clear or not clear? Inshallah bulila. Okay, this is I skip this one. We calculate one more time theoretical oxygen demand, maybe more easier. This is for sugar. You know the chemical composition of sugar? Tatahu. How much you drink every day sugar? About 100 gram. Or how much? With chocolate, with ice cream, with this, maybe if more than 50 will be secret masala. Try to take care of sugar, huh? Because diabetes will be there in the future. You are still young. Try to take care of yourself. Maximum recommended sugar amount every day for us is about 30 gram only. So don't take too much. Maybe because of COVID-19 and you are MCO, you feel little bit stressed, you drink more sweet, you eat more sweet. Be careful, huh? Inshallah, this problem will finish soon, inshallah. So here, I want to calculate theoretical oxygen demand for sugar. The chemical composition is 612 H22O11. Dissolved in water to a concentration of 100 milligram per liter, or this is 100 ppm, and needs to calculate also TOC. So I need two things to calculate: theoretical oxygen demand and also total organic carbon. Okay, we go one by one. First of all, I need to make a balanced equation. So C12H22O2 plus oxygen will give me this, meaning combustion, meaning that burning. How much oxygen needed? This will be burning, combustion. Combustion, usually we burn with air. Like charcoal, when we make barbecue, we use air, oxygen, and this carbon, charcoal, change to carbon dioxide. So this is similar. But here I want to calculate how much oxygen needed. So it will give me CO2 plus H2O. How to calculate theoretical oxygen demand? I will take this 12 mole O2 multiply by 32 gram. So this now became a gram. This 1 mole will be molecular weight. This molecular weight will be 342. You make summation, you will get 342. So results will be 1.123 gram O2 divided by 1 gram sugar. This already changed gram. If I want to change to milligram per liter or part per million, machamana, I will multiply here by 1 million. I divide here by 1 million and I calculate. Okay, so I will get here big value. Okay, or here, if I want to change gram to milligram, how I can change theoretical oxygen demand will be 100. I have here 100 milligram per liter. Okay, this is gram per gram sugar, but here I have 100 milligram. So I don't have 1 gram. I have only 0.1 of gram. So I need here to divide by 0.1. Hopefully you understand. So here 100 milligram per liter multiplied by 1.123 gram O2, and this multiply, I change from gram to milligram. Finally, my results will be 112.3 milligram O2 per liter from here. Try to make it. If you cannot, we okay or not okay? I think unit conversion you studied and boleh tak boleh? Boleh? Boleh tak? I have here gram O2 per gram sugar, and I have here 100 milligram per liter. So here I want to divide milligram sugar, but this I need to change to milligram to take milligram per milligram. So I need to multiply by 1000 to change here. Understand? Then finally I will get 112 milligram O2 divided by liter. Okay, here I want to calculate how much oxygen per liter needed. Okay. For TOC is very easy. TOC, I mean, I need to calculate how much total organic carbon. I have how many carbon? I have 12, right? What is the molecular weight of carbon? Also 12. So 12 multiplied by 12 will be 144 gram. This will be 144 gram in 342 gram sugar, because I have 1 mole here. So I will get 0.42 gram carbon divided by gram sugar. Okay. So can I calculate TOC? I can calculate. It will be 42 milligram carbon per liter, because I have here 100 milligram per liter sugar. So I can calculate how much TOC. Kalau tafaham, maybe we can discuss next time during review or any time, but hopefully you understand a little bit, huh? Another example, how to calculate chemical oxygen demand and total organic carbon. This BOD5 and this I will make here very short, but in next chapter we'll go for details, how to draw from scratch, how to make, how to take samples, how to measure every day for 5 days, and from dissolved oxygen, how to calculate BOD. We will see macam mana lah. Here, chemical oxygen demand and total organic carbon, how to calculate, determine BOD5, COD, BOD5, TOC, TOC, COD ratios for the following organic compounds, and it is given C5H7NO2. Assume K equal 0.23 per day, and assume the organic compound is completely biodegradable. When it is completely biodegradable, meaning that theoretical oxygen demand equal chemical oxygen demand equal ultimate biological oxygen demand. Okay, this true when compound is completely biodegradable. We'll see how. First of all, we calculate COD, how much chemical oxygen demand. So this compound, again, I need to make balanced equation. Okay, so molecular weight of this compound, it is 113, and this 5 oxygen atom molecular weight is 160. So COD will be oxygen here mole, be careful, this is 5 mole, this 160 will be because I multiply this 5 by molecular weight, this will be gram. But this is mole. This one is mole. This one is 1 mole. This one 2 moles. Here 1 mole. Be careful. So here I already changed. This is 1 mole C5H7NO2. I change it to 113 gram because I take the molecular weight. Here 5 mole O2 I multiply by molecular weight became 160 gram. So COD will be 160 weight of oxygen divided by weight of the compound, which is 113. So I will get 1.42 milligram O2 divided by milligram C5H7NO2. You can make also the same. You can start from here, 5 divided by 1, and then you change also Bole. You can make table and you change based on molecular weight. What about BOD5? I can calculate BOD5 because BOD5 divided by ultimate BOD equal 1 minus, this is equation will be given. This 5, it means 5 days. Okay? So BOD5 will be ultimate. Ultimate BOD will be? No, ultimate. This BOD5 divided by ultimate BOD will be equal this amount. If I calculate this one, because it's given K 0.23 and time also given, this 5, so I will get 0.68. Okay? So BOD here, BOD5 will be ultimate BOD multiplied by 0.68. Here COD is equal ultimate BOD. So BOD5 will be 0.68 multiplied by 1.4 here. So I will get 0.97 milligram BOD per milligram compound. How to calculate total organic carbon of the compound? Here, how many carbons I have? I have here 5. 5 multiplied by 12, how much? This will be 5 multiplied by 12 divided by 113. 113 is the molecular weight of the compound. I will get 0.53 milligram TOC divided by milligram C5H7NO2. Now, if I want to calculate BOD5 divided by COD, I just put the values here, in here, and then I will get the final results. If I want to calculate BOD5 divided by TOC, I will get 1.82. If I want to calculate TOC divided by COD, I will get 0.37. So here, this information is very important. If it is completely biodegradable, meaning that COD equal theoretical oxygen demand equal ultimate BOD. Okay. Hopefully you understand. Shikat okay? Ta okay? I think this is the end for today. But if you have any question, I can answer you, no problem. Anything about chemical? Today our focus about chemical. Any problem with chemical? Ada masalah? Tak ada masalah?
No, sir.
No, sir. You want to go Makan, I think. You are very hurried to go Makan.
No.
It's okay, you can go, no problem. So study, I will send you this lecture notes. I will send you today. And here very important because I don't want you to repeat, because here already I show you before. This one, coagulation experiment, there is in YouTube, you can watch. To people who don't watch to understand, you can go and watch. Okay, there is one coagulation experiment, wastewater by Salahuddin written. You see that one. You will understand what is the meaning of suspended solid here and how to remove this suspended solid. And for industrial application, SiO2 removal. This SiO2 used in motherboard of our PCs, all electronic using this. So it is a huge amount of silica and it is very suspended, very minute, very small, very nano-sized particles, difficult to remove. So we make coagulation and details of that experiment. That one I did before in Japan, but I like to share with you how we make. You can see that slides for just more information. Okay. I think that is all for today. Hopefully you go for problems, and because I will give you assignment, I make sure that you understand assignment very clearly, especially problems. Okay. Enough. No question. The other question. The other question. No problem. No answer. Maybe already left all of you. Okay. 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 See you. Assalamu alaikum wa rahmatullahi wa barakatuh.
Waalaikumsalam. Thank you.
Waalaikumsalam, sir.